So, good afternoon. My name is Nikita, and despite working on Kotlin at JetBrains, I'm guilty of writing Swift in my spare time. That's why today I'm doing the weirdest thing. I'm giving a talk about Swift at Kotlin Conf. But don't boo at me yet. You will have an opportunity to do so at the end of the session. OK, but on a serious note, I have a couple of reasons to talk about Swift here. So the first one is that the standout feature of the latest major Swift version is a strict concurrency mode, which aims at preventing data race safety if you do it right. And given the similarities between Kotlin Coroutines and Swift concurrency, it's worth to take a look at how Swift implemented that. And it's beneficial for you to learn more about Swift before you decide to interop with it. Kotlin is a multi-platform language, remember? And Swift expert is coming. The good news is that you already know a lot about Swift concurrency just because of how they similar are to the Kotlin coroutines. Similar to how you declare a suspend function in Kotlin, you declare a sync function in Swift. Similar to how you only allowed to call suspend functions only from other suspend functions, you're allowed to call async functions only from other async functions, except in Swift you have to prefix the function invocation with the await keyword as an act of acknowledgement that the operation is non-atomic. In Kotlin, we believe that it's just enough to show you a gutter icon in ID instead. Similar to how you can suspend your coroutine to get a continuation to use it to interop with some callback-based APIs or to program effect handlers, you can do the same in Swift. Continuations in both languages are one-shot, meaning that you have to call resume exactly once. Similar to how cancellation in Kotlin is cooperative, meaning that you have to periodically call ensure active, cancellation is cooperative in Swift, meaning that you have to call check cancellation periodically, except in Swift all exceptions are checked, meaning that you have to prefix the function invocation with a try keyword. And you can have both keywords, try and await, meaning that your computation is asynchronous and probably it's cancelable, but not guaranteed because it could be thrown some other exception. And if it's only one keyword, it's for sure non-cancelable. Similar to how, well, both languages endorse structured concurrency by default, so meaning that your computation form and parent and child relation, which are on a bigger scale, forms a big asynchronous tree of computation. So for example, it means that the parent has to wait for all of its children by default. So here we have the first children that waits for 1 second, the second child waits for 3 seconds, meaning that the parent has to wait for its longest child for 3 seconds, meaning that we will never hit the assertion at the end of the function. And just another example on the structured concurrency is cancellation. When the parent cancels its execution, it means that we have to firstly cancel all children execution to make sure that the whole subtree of computation is shut down. So for example, here we have 2 children. Each of them wait for 10 seconds, but just in 1 second, the parent cancels its execution, meaning that neither of the child will have an opportunity to wait for all 10 seconds, and we will have to print or cancel. Well, yeah. Hopefully you didn't get bored, because now we're getting into interesting stuff, how Swift 6 implements data race safety prevention. So data race safety, you say, huh? What happens if we declare a global mutable variable? We all know that the global mutable state doesn't go well with concurrency. And in Swift 5.9, it's perfectly fine. It's a green code. But in Swift 6, it's a compilation error. And you have 3 ways to fix it. Well, the first one, you can obviously convert your mutable variable to a mutable one. Or you can keep it mutable, but you have to annotate it with the @main_actor annotation, which will make sure that the variable is only accessible from the main thread. So for example, if we try to access it from another function, Swift would get angry at us and ask to annotate that function with the @main_actor as well, meaning that the annotation is poisonous. And as you might have guessed already, the main function is implicitly annotated with the @main_actor annotation. And the third option you have is to use non-isolated unsafe keyword, but you're only allowed to use that if you can swear on your life that you know how to use synchronization primitives. So as you saw, Swift 6 strict concurrency mode is really strict. Essentially, they did a break and change on global mutable variables. And here I'm curious to see how many of you would be OK if we did such change and broke global mutable variables in exchange for data race safety. Actually, I would say not that many of you, less than a half. You see, that's why we can have nice things. Because backwards compatibility. Jesus. Okay. Let's try to keep breaking Swift. Here we have a immutable global variable, but inside of it we have a nested mutable state, and it's red code. And we have two ways to fix it. We can either use @main_actor notation as previously, or we could inherit from the sendable interface, or if we were to speak Swift language, conform to the sendable protocol, which will make sure that our class is thread safe, meaning that it's not allowed to have mutable state inside of it. Just another example on trying to break Swift. What happens if we try to share a reference to a mutable object to another thread? So here we have a bank account variable, and it's captured by two lambdas, the for each lambda and the lambda that we pass to the constructor of the thread class. And obviously the first one is OK, because the lambda is called in place. But the second one is not, because it's executed in parallel. And Swift correctly identifies that. It only highlights the second usage of the variable. But how does it do that? How does it determine that the first one is OK, but the second is not? Well, if we look at the definition of the functions, definition of the for each function and the thread constructor, we will see that the functional type, in case of the thread constructor, is annotated with @sendable notation, meaning that the lambda is only allowed to capture sendable objects. And it all makes sense. You're constructing an object on one thread and sending it over to another to execute there, and for that it has to be sendable, right? So the last topic I want to cover is actors. What is an actor? The idea is that if you have a mutable state and you have a concurrent system, instead of making your mutable state global, you isolate it to small islands of isolation, concurrency domains, which we call actors. And those actors are sole owners of that mutable state. And only them are allowed to access that mutable state. They prevent others from accessing that. And actors themselves, they communicate by means of immutable messages. So, and each actor is single-threaded. That's why it's safe for it to have its internal state mutable. So remember that example from previous slide? Of course, we want to keep age variable mutable because Cody will grow up. So another option that we have is to change our class to actor. And in that case, sendable conformance is optional because all actors are sendable implicitly. And yeah, and we'll keep going. So we complicate our example a bit. Now we have mutable state inside of actor of mutable objects. And we will see how actors protect the internal state that they isolate. So if we declare a function inside of an actor, that function is executed on that very same single thread. That's why it's safe to access the internal state of the actor. And that code is perfectly fine. But if we try to declare the very same function outside of an actor, well, the first thing you notice is that Swift will require you to put an await keyword, because calling properties on an actor or calling functions on an actor is similar to sending a message on an actor, as we saw in the classic actors model. And for that, you have to yield to send a message, then to receive a response, and then continue your execution. But even so, this code is red, because task property, its return type is a mutable state, which leaves its isolation domain, and generally it's not allowed to share mutable state outside of the boundaries of the actor. So that's how actors protect the state inside of them. Okay, so now when we saw how actors do that, let's try to send a proper message to an actor. For that, we declare a function with a parameter. When we call that function, we, as we know, have to put an await keyword, even so the function itself is not async, because we're calling from the outside, right? And you see here, the parameter is a mutable class. And as we saw, it's not allowed to, well, actors should communicate by means of immutable messages. So this code apparently should be read, right? Wrong. And the reason for that is because Swift is just too smart. Here we constructed an object to do item, and then we send it over to an actor. We send in a message, it leaves the previous isolation domain and gets into the isolation domain of an actor. We never access that object anywhere where it was constructed. But if we try to access that object just after we handed it over to an actor, that's the moment that Swift would get angry at us. So the idea here is that messages either must be immutable or they must leave the previous isolation domain. And you also notice that if you change the variable to a parameter, in that case, you will get the very same compiler error message because, well, Swift doesn't know if the function is a sole owner of that parameter. It could be also shared with another isolation domain, right? And thankfully, Swift has a way of expressing that. So you can put a sending keyword there to say that you're a sole owner of an object. Yeah, and all works fine. Meaning that the add member function, the parameter task inside of it, has been sending for all this time implicitly. Hopefully you can see the beautiful symmetry here. I'll give you a couple seconds to process. OK, so conclusions. At Kotlin, we keep an eye on other programming languages. And Swift, in particular, is interesting to us because its concurrency model is similar to the one in Kotlin. Swift went from a language with no data array safety guarantees, the position that Kotlin is currently in, to the language that provides that array safety guarantees. And, well, Swift interrupts with Swift. Well, Kotlin interrupts with Swift. I congratulate the Swift team with delivering the feature. I'm sure that a lot of effort has been put into it. And the closest that we are doing right now in terms of research is deep immutability, which is an important step forward towards an ergonomic data array safety. That's all. Thank you for coming. And now you can boo.